All right, everyone, welcome back to Aerominds Training Center. And today we are going to talk about the subsonic airflow part 3. And the chapter is 4 of the principles of flight. And we have already done two parts of this chapter. And we are on the last part, which is the third part. And so we are going to talk about something known as pressure gradient today, which is a very important concept in aerodynamics. And also, it directly connects to airflow over the wing, the boundary layer behavior, and also finally the stall, which is obviously one of the most important topics for your exam and also for your safe flying. So, firstly, we'll understand the word pressure here. Okay. So, now pressure, we'll see. Now, first, we see if the air, we know the air has weight. And because the air has weight, it presses on everything. Okay. And that pressing force per unit area is called the pressure. Force per unit area, pressing force, okay, is known as the pressure. Okay, now imagine you move from one point in air to another point in the air. Okay, if the pressure at the second point is different from the first, if the pressure at the second point is different as the first, what will happen? Then we can say that there is a change in pressure over distance. We have traveled some distance and there is a change in the pressure. Now that change in the pressure over a certain distance is called pressure gradient. Okay, so in simple words, if you call it a pressure gradient, means pressure is not same everywhere, it is changing as we move along. Got it? So remember this, a pressure gradient is a change in the air pressure over a distance. And now the greater pressure difference between the 2 points, the steeper will be the pressure gradient. Okay, now think of a hill like this. Okay, and if the height changes very slowly, it's a gentle slope like this. Okay, and if the height changes very quickly, like this, it's a short distance, it's a steep slope. Okay, the pressure gradient is exactly like that, but instead of the height, we are talking about the pressure here. So big pressure change in a short distance means a steeper pressure gradient. Got it? Now we'll connect this airflow over the wing or the aerofoil. So first we'll mark this. A pressure gradient is a change in the air pressure over a distance, and the greater the pressure difference between 2 points, the steeper will be the pressure gradient. Got it? Now, what happens when, see, when air flows over a wing, the pressure does not stay the same all over the surface. Okay, it keeps on changing. So in some regions, the pressure decreases. The pressure decreases in the direction in which the air is moving. Okay, and in some regions the pressure increases in the direction in which the air is moving. Okay, now these two situations are extremely important and they have some special names. So first we'll talk about the favorable pressure gradient. So see, basically a favorable pressure gradient exists when the pressure is decreasing in the direction of the airflow. Remember this. Okay, so imagine air is moving from, suppose this is your aerofoil, from suppose air is moving from leading edge to trailing edge. Okay, now if as it moves forward, what happens? Pressure keeps becoming lower and lower. Okay, then the pressure gradient is favorable, you can say. Now why do we call it favorable? Because this condition helps the airflow. When pressure is decreasing in the direction of the motion, the air particles will feel like they are being pulled forward. Okay, they are moving from a higher pressure region to a lower pressure region, and nature always wants to go from higher pressure to low pressure, like that. Okay, so the air is happy to move, to keep moving forward. Okay, so because of this, the airflow tends to remain smooth, and basically smooth airflow means the air layers are sliding nicely. Okay, like this. Also, the airflow keeps attached to the aerofoil. So for example, we'll see this aerofoil. Smooth airflow is like, will be like this. It will be sticked to the surface of the aerofoil. Okay, and it follows the shape, the contour of the wing without breaking away. It is very important for your uh, for the production of your lift very efficiently. So a favorable pressure gradient exists when air pressure is decreasing in the direction of the airflow. Okay, and this condition helps in the airflow to remain smooth and also to remain attached to the aerofoil surface. Now we come to the opposite case, which is called the adverse pressure gradient. Adverse pressure gradient. Now see, an adverse pressure gradient exists when air pressure is increasing, when it is increasing in the direction of the uh, airflow. Okay, now again imagine air which is moving from leading edge to trailing edge. Air is moving from here to here, from leading edge to trailing edge. Okay, and if as it moves forward, the pressure starts increasing. Okay, and then the air is now trying to go from a lower pressure region to a higher pressure region. Okay, and that is not natural for the air, you can say. So it is like you are trying to walk uphill instead of downhill. Okay, and also a common example of this on a wing is the region between the point of the minimum pressure on the upper surface here, minimum pressure, and the trailing edge. Okay, and on the top of the wing the pressure reduced to a very low value somewhere near the front part. So we'll see a diagram for this like this: the adverse pressure gradient, the trailing edge, and the minimum pressure. So this region is called the adverse pressure gradient region. Got it? So this condition is actually opposing the airflow. An adverse pressure gradient exists when air pressure is increasing in the direction of the airflow. Example: between the point on the minimum pressure on the upper surface and the trailing edge. Okay, now this condition is opposing the airflow. Now the air is actually losing energy as it is moving along the surface. Okay, especially near the surface where the boundary layer is existing. So because the pressure is increasing ahead, the air will slow down. Pressure increases, velocity decreases. Okay, so if it is slowing down too much, it may have not enough energy to keep moving forward along the surface. Then something very important and very dangerous can happen: the airflow can separate from the surface. This condition opposes the airflow and makes it harder for the air to continue moving forward. Okay, now we bring in the angle of attack, which you already know is the angle between the chord line and the relative airflow. So as the angle of attack increases, the angle of attack increases, the pressure gradient becomes steeper. Got it? Now this means that both the drop in the pressure near the front and the rise in the pressure towards the back become more extreme. Now the suction at the top surface will become very stronger, and the recovery of the pressure towards the trailing edge will become more difficult here. Okay, it will become more difficult here. So uh, at angles of attack which are greater than 16 degree approximately, for many typical aerofoils, you can say the adverse pressure gradient becomes extremely steep, and the number is not just magic for every wing, but for the exam purpose around 15 to 16 degrees is the commonly associated with the with your critical angle of attack. Okay, and as a result, the what will happen? So at such high angles of attack, the air flowing which is over the upper surface can no longer follow the airfoil contours. It cannot follow. So the boundary layer, which is already low in energy, what will happen? And low in energy, which is due to the friction, cannot fight against the rising pressure. Okay, the pressure is rising at the trailing edge, so it stops moving forward and starts to reverse locally. Okay, so as a result, what will happen? The flow separates from the surface. Now what happens? It will lead to a stall. So as the angle of attack increases, the pressure gradient becomes steeper. Okay, as the angle of attack greater than 16 degrees, the adverse pressure gradient becomes extremely steep. Air flowing over the upper surface can no longer follow the aerofoil contour, and it will separate from the surface when you increase your angle of attack. Then comes the flow separation and stall. So when the flow separation occurs, the previously smooth streamlined flow breaks away from the surface. It will break away from the surface, and instead of the air which is nicely hugging the top of the wing, now it will get a big region of the disturbed, swirling, you can say turbulent flow, like this. Okay, so this separated flow cannot produce the same low pressure that is smooth fast flow could produce. Okay, so because of this, the low pressure area on the top surface will suddenly collapse, and earlier most of the lift was coming from very low pressure on the top and relatively high pressure below. Now the top surface is no longer giving you that strong suction. Now as a result, what will happen, any remaining pressure differential uh, is only due to the increase in the pressure on the lower surface. Now that is much smaller compared to the earlier total lift. So the total lift will drop suddenly, okay, and very significantly. So this condition is known as stall. And for exams, always remember that stall is not directly associated with speed. It is also about exceeding your critical angle of attack. Critical angle of attack, which causes your flow separation and also sudden loss in your lift. Got it? So remember this, when flow separation occurs, the previously smooth streamlined flow breaks away. The low pressure area on the top surface will suddenly collapse, and as a result, any remaining pressure differential will be only due to the increase in the pressure on the lower surface only. Okay, and this condition is known as stall. So now we'll move forward for the definition of center of pressure. Okay, now even though the entire surface of the aerofoil is contributing for the lift, but we often want to simplify things. Okay, so instead of thinking that lift is spread everywhere, we imagine that the total lift force acts at a single point only. Okay, which is along the chord line obviously, and that imaginary point is known as the center of pressure, so CP. So the center of pressure is actually the point along the chord line where the distributed lift is considered to be acting, called the center of pressure. So remember this, although the entire surface of the aerofoil contributes to the lift, but the point which is along the chord line where the distributed lift is considered to act is called the center of pressure. This is your center of pressure. Now we'll see the factors which are affecting the CP location. Okay, so basically the position of the center of pressure depends upon the camber of the aerofoil, your camber, which is the difference between the camber line and the chord line. Okay, and camber basically means how curved the aerofoil is. More camber means more camber changes how pressure is distributed over the surface, and that changes where the resultant lift will be acting. Okay, then it also depends upon the section lift coefficient. Now that is a measure of how much lift the aerofoil section is producing. Okay, and this lift coefficient is directly related to your angle of attack. So in simple words, if you ask, when angle of attack changes, the lift coefficient will change, and that changes the pressure distribution, which will move your center of pressure. That is it. So remember, the position of the CP depends upon the camber of the aerofoil and also your section lift coefficient, which is directly related to your angle of attack. Okay, now we'll see how the center of pressure moves. So at as the angle of attack increases from 0 degrees to 16 degrees, 0 degrees to 16 degrees, what happens? The upper suction peak, the upper surface suction peak moves forward. Okay, that means the lowest pressure point on the top surface will shift closer to the leading edge. We'll see this. So you can see this like this. Suppose you are from 0 to 8 degrees. At 8 degrees, your upper suction peak will be somewhat here. Okay, this is your aerofoil. This is your angle of attack. This is your relative airflow. This is your chord line. So this will be your upper suction peak, and it will be moving forward here near the leading edge. This is your leading edge. Got it? So because of this forward motion of the suction, what will happen? The upper suction peak moves forward, therefore the center of pressure also move forward. So the forward movement of the suction, the center of pressure also move forward along the cord. Now at the same time, the magnitude of the lift will also increase. Magnitude of the lift will also increase. So as you increase your angle of attack in the normal operating range, your lift will increase, okay, and your CP will move forward. Okay, and just before the stall, the lift will reach its maximum value, which is the CL max, or the maximum lift coefficient. Now at this point, the center of pressure is at the most forward location. So we'll see the next one, which is 14. So you guys can compare this. At 14, at 8 it was here, and 14 it will be somewhat more front, near the leading edge. It will be more closer to the leading edge. And then afterwards, after the stall, the lift will decrease abruptly because of the flow separation, of course. And when that happens, the pressure distribution changes very dramatically. The suction on the top is reduced, the center of pressure generally moves rearwards along the cord, and this rearward movement can affect the pitching moment of the aircraft as well, which is very important for your stability and control, which we'll study in later chapters. Stability. Okay, so remember this, when you increase this more CP beyond the critical angle of attack, the lift will collapse and the CP will move rearwards at 16 degrees angle of attack. So remember this, as the angle of attack increases from 0 degrees to 16 degrees, the upper suction peak moves forward. Therefore, the center of pressure also moves forward. At the same time, the magnitude of the lift will increase, and just before the stall, the lift will reach its maximum value, which is CL max. And the CP at its most forward location will be just before the stall. And after the stall, what will happen? The lift will decrease abruptly, and the CP generally moves rearwards along the cord. Now we'll move to a new concept, which is what is coefficient. Now, coefficient is actually a dimensionless number. Dimensionless number, and that basically expresses the degree of the magnitude of a quantity. Now dimensionless means no units, okay, no meters, no seconds, no kilograms, just a pure number. And in aerodynamics we use force coefficients to make life easier, you can say. So an aerodynamic force coefficient allows comparison between the aircraft of different sizes, different weights, and different speeds. And without coefficient, a big aircraft will have a bigger lift and drag numbers than a small aircraft, which is not useful for the comparison. So we use the coefficient as a common reference. Okay, we'll mark this. A coefficient is a dimensionless number that expresses the degree of the magnitude of a quantity. An aerodynamic force coefficient allows a comparison between the aircrafts of different sizes, weights, and speed, and it acts as a common reference. Now, see, an aerodynamic force coefficient is actually a dimensionless ratio. Aerodynamic force coefficient is a dimensionless ratio, and between the average, you can say the average aerodynamic pressure which is acting on a surface and the dynamic pressure of the stream. Between the average aerodynamic pressure and the dynamic pressure of the airstream. Okay, so dynamic pressure depends upon the air density and the square of the speed. So when we divide the actual aerodynamic force by the dynamic pressure, and by a reference area, we remove the direct effect of the speed, density, and the size. Okay, what remains mainly depends upon the shape and the angle of attack only. So remember this, an aerodynamic force coefficient is actually a dimensionless ratio between the average aerodynamic pressure and the dynamic pressure of the airstream. Okay, so now we define the lift and the drag coefficient. So the lift coefficient, which is CL, is equal to lift divided by the dynamic pressure multiplied by wing planform area. Okay, and the wing planform area basically means the area of the wing which is seen from the above, like this. This is your fuselage, like this. Okay, then comes the drag coefficient, which is CD. So it is the drag which is divided by the dynamic pressure multiplied by the wing planform area. Okay, so for your exams, just You must remember these relationships. Even if the exact formula is not us, the concept is very important. Okay, so remember this: lift coefficient, which is CL, and drag coefficient, which is CD. Then comes why force coefficients are used. Okay, so aerodynamic force coefficients are basically necessary because they are independent of the wing area. Okay, they're independent of the wing area, the air density, and the airspeed. Okay, this is very important. It means that the CL and the CD do not directly change just because the aircraft is bigger or it is flying faster. Okay, those effects are already accounted in for the dynamic pressure and the area in this and this. Okay, so but these coefficients are actually dependent on the shape of the surface and the angle of attack. Okay, these factors are determining how the pressure is distributed over the surface, and that pressure difference, distribution will in turn determine the lift and drag. Okay, so in simple words, the coefficient basically tells you how good a shape is at basically producing lift, or how much drag will it create, without worrying about the size of the speed or the speed. So this is why they are so powerful and so widely used in your aerodynamics and also in your exams. So the use of aerodynamic force coefficient is necessary because they are independent of these things, and they are dependent on the shape of the surface, angle of attack. So these factors determine the pressure distribution, which in turn determines the lift and the drag. Got it? So now we'll move further, which is the pressure distribution and pitching moments. So when the air flows over an aerofoil, the pressure is not the same everywhere. Some areas will have high pressure, some areas will have low pressure, and this pressure distribution over the surface of the aerofoil does two main things. Now first, it produces aerodynamic force. The most important aerodynamic force for us is the lift. Okay, now lift is simply the result of the high pressure of the on the one side and low pressure on the one side of the wing. So but that is not all. Okay, the pressure distribution also produces the aerodynamic moments. A moment is a turning effect, you can say. Now in this case, we are interested in pitching moment. Okay, which tries to rotate the aerofoil nose up or nose down about some reference point. So now there are two ways to understand how how a change in the angle of attack is affecting the pitching moment of an aerofoil. There are two ways. So the first way is to think in terms of the lift acting through a moving center of pressure. Okay, now as angle of attack changes, the lift changes, and the center of pressure also moves forward or backward. Now the because the force and the point where it acts, both are changing, the turning effect or the moment will also change. Okay, and the second way is simpler and more useful for your exam and also for your theory. Now so we imagine that all the changes in the lift happen through a fixed point, which is called the aerodynamic center. Okay, so this makes the math and understanding basically your tech gen most easily. Okay, so instead of worrying about a moving center of pressure, because center pressure is constantly moving with the change in angle of attack, so we use a fixed point and say lift changes around that point only. Okay, so, the distribution of the pressure over an aerofoil produces aerodynamic forces, which is lift, and also produces aerodynamic moments like the pitching moments, nose up or nose down. So, there are two ways to understand how a change in angle of attack is affecting the pitching moment of an aerofoil actually. So, the change in the magnitude of the lift, which is acting through a moving center of pressure, or more simply, the change in magnitude of the lift through a fixed aerodynamic center, which is AC. Okay, so we'll understand clearly what AC is, aerodynamic center. So aerodynamic center is basically a fixed point on the chord line, fixed point on the chord line, okay, of the aerofoil. So the chord line, remember, is the straight line joining the leading edge and the trailing edge. Okay, so the aerodynamic center is defined as the point where all the changes in the magnitude of the lift effectively takes place. Okay, so in other words, you can say when angle of attack changes, the lift increases or decreases. We can imagine that this change in the lift is acting at the aerodynamic center. Okay, and it is also defined as the point about which the pitching moment remains constant at normal angles of attack. Okay, now this is extremely important for your exam. No matter how much you change the angle of attack within the normal range, or normal unstalled range, you can say, the pitching moment about the aerodynamic center does not change very significantly. Okay, it almost remains constant. So remember this. The aerodynamic center is a fixed point on the chord line, and it is defined as the point where all the changes in the magnitude of the lift take place, or the point about which the pitching moments remain constant for the normal angles of attack. Now comes the pitching moment about the aerodynamic center. We'll see the aerodynamic center first. So this is your image for an aerodynamic center. This aerodynamic center, and this is your CG, and this will be a change in the lift. So we'll talk about the pitching moment about the aerodynamic center now. So see, a nose down pitching moment exists about the AC. So see, for most of the cambered aerofoils, a nose down pitching moment will exist. Okay, now nose down basically means the moment tries to rotate the nose of the airfoil downward. Okay, nose down pitching moment. Okay, now where does this pitching moment come from? Okay, it is produced by the lift which is acting at the center of pressure. It is produced by the force which is the lift acting at the center of pressure, which is not at the same place as the aerodynamic center. So we have a force which is lift, and then we have a distance between where the force acts and the center of pressure and our reference point, which is the aerodynamic center, and this distance is called the moment arm. Okay, so moment is actually moment is equal to the force multiplied by the distance. Okay, so the lift times the distance between the CP and the AC will give you the pitching moment. Lift multiplied by the distance between CP and AC, which is D1, will give you the moment. Okay, so remember this. A nose down pitching moment exists about the AC, and this pitching moment is produced by two things. First, the force, which is the lift acting at the center of pressure, and the moment arm, which is the distance between the CP and the AC. And as the angle of attack will increase, as the angle of attack increases, the lift force increases, and the CP moves forward towards the aerodynamic center, and the moment shortens. So see, if you compare this with this, so the CP was here and it is now come forward when the lift increased. So the distance between the two decreases. Okay. So see what happens during the increase in the angle of attack. As the angle of attack increased, the lift force increased. Okay. And at the same time, the center of pressure moved forward. And this means the distance between the AC and the CP becomes smaller. So the moment arm will become smaller. Okay. So we have two things happening together. The force is increasing, but the lever arm is decreasing. The force is increasing, but the lever arm is decreasing. And these two things happening together will cause a effect which will almost cancel out each other. Okay, and because of this, the pitching moment which is about the aerodynamic center will remain constant within the normal angle of attack range. Okay, it's a very important concept. Remember this. The pitching moment about the aerodynamic center remains constant within the normal angle of attack range. Got it? So even though if the lift is changing a lot with the angle of attack, the pitching moment about the aerodynamic center will remain the same because it is cancelling out each other. Then comes the location of the aerodynamic center. Okay, so for the subsonic airflow at speed less than zero point 0.4 Mach, the aerodynamic center is located about 25% of the chord from the leading edge. Leading edge is front. So that means if you measure the chord from front to the back, one quarter of the distance, one fourth of the distance, which is 25%, uh, the distance from the leading edge is the aerodynamic center. Okay, so for your exam purposes, you must remember this. For subsonic airflow, at speeds less than 0.4 Mach, the aerodynamic center is located at the 25% of the chord from the leading edge. Okay, and this is true for any aerofoil regardless of the camber. This is true for any aerofoil regardless of the camber, regardless of the thickness, and also regardless of the angle of attack. Okay, so this is why the aerodynamic center is such a useful reference point, you can say. Now comes the importance of the aerodynamic center. So the aerodynamic center is the key aerodynamic reference point, and it is the most important application is in the longitudinal stability of the aircraft. Okay, now longitudinal stability means the stability in the pitch means up and down of the nose. Okay, nose up or nose down motion is known as pitch. And when the designers basically decide where to place the wing, where to place the tail plane or the center of gravity, they use the aerodynamic center as the reference. The designer use the aerodynamic center. Okay, so the aerodynamic center is the key aerodynamic reference point. Its most important application is the longitudinal stability of the aircraft. Then comes the pressure distribution in a symmetrical aerofoil. So a symmetrical aerofoil is basically the one where the upper and the lower surface are the mirror images, you can say the mirror images of each other. There is no camber and it looks the same up or down. Up on the top of the side and on the bottom of the side, they look similar. So first let us see the pressure distribution in a symmetrical airfoil at zero angles of attack, then we'll increase it. So at the zero angle of attack, at 0 degree angle of attack or 0 degree angle of attack, the airflow sees the top and the bottom surface exactly the same. Okay, the upper and the lower surfaces are equal. So both the pressures on the upper and the lower surface will be equal, and because these pressures are equal, the force which is acting will be equal and at the same location. Okay, therefore the net pitching moment will be also zero. Okay, so there is no turning effect which is trying to rotate the aerofoil. Got it? So for a symmetrical aerofoil at 0 degree angle of attack, the upper and the lower surface pressures are equal. The force acts on the same point and the net pitching moment will be zero. See this. Okay, for a symmetrical airfoil will be equal. So they'll cancel out each other at zero lift angle of attack. Now comes the effect of increasing angle of attack. Okay, so see, as the angle of attack increases, the upper surface pressure decreases and the lower surface pressure increases. Okay, compared to the top. So lift will increase. Now, however, for a symmetrical airfoil in the normal range of the angle of attack, the center of pressure does not move very significantly. It stays near the same position only. Now, this is a special characteristic of the symmetrical aerofoils. And what happens in a cambered aerofoil? The center of pressure moves with the angle of attack. Okay, in symmetrical aerofoil, it always remains the same. So upper surface force increases, lower surface force decreases, and the result is that the lift will increase and the center of pressure does not move. This is a special characteristic of a symmetrical aerofoil. Then comes the pitching moment about the aerodynamic center. Okay, now if you think about this, the lift changes as the angle of attack increases. Lift changes, but the center of pressure almost the position almost remains fixed. Okay, and the aerodynamic center is also the same quarter chord position, which is 25% around 25%. So because of this symmetry, what will happen? The pitching moment about the aerodynamic center will remain zero at the normal angles of attack. Okay, and it's a very big major advantage for the symmetrical airfoil that zero pitching moment about the center of pressure over the normal operating range of the angle of attack is happening. Okay, this means that they do not naturally try to nose up or nose down as the lift will change. Okay, so this gives you a stable and a very predictable pitching behavior. Okay, and which is actually why the symmetrical airfoils are often used in tail planes and all the control surfaces where the predictable behavior is very important. So symmetrical aerofoil at positive lift. Okay, the aerodynamic center, this is the lift, this is the more pressure. Okay, so remember this. Since the lift changes, the CP position almost remains fixed for symmetrical aerofoil. The pitching moment about the aerodynamic center remains zero at the normal angles of attack. These are the properties of a symmetrical aerofoil. Then advantage. So one major advantage is the zero pitching moment about the aerodynamic center and over the normal operating range of the angle of attack. This makes it especially useful in control columns, or you can say the control surfaces. The control surfaces have uh, are symmetrical aerofoils. So now we have completed our chapter, and we did each and every part of this subsonic airflow chapter. And now we are going to start with the uh, MCQs, which are according to the which comes in the exam. Okay, so there are around 140 150 questions, and each of the question is very important. So you can start now. Position of the camber, symmetrical airfoil, thickness distribution, leading edge radius effects, relative airflow, how is it flowing, magnitude of the relative airflow, lift and drag, how are they connected, lift acts where, relative velocity, in actual flight conditions, what happens, then three-dimensional airflow exists where, it consists of what is span-wise flow, what is 2D flow, what is upwash, what is downwash, after passing over the aerofoil, what happens, static pressure on one side of the body reduced, what happens, pressure difference, relative airflow remaining the same when, all of the questions are included in this. Angle of attack increases, what happens to stagnation point, ice frost, dust, everything, what affects the leading edge. Once you are done with all these questions, you are good to go for this chapter, and there's nothing much left to this now. So whenever you are done with this chapter, just tell me and I'll post the answers for this chapter. And if you want any personal guidance or any doubt you have, you can text me on Instagram, or you can comment in the YouTube comment box, and I'll upload a particular video according to that. So that is it for this chapter. Now we'll see you in the next chapter, which is chapter 5, lift, um, prepared by the Aerominds Training Center. So take care, guys, and thank you.